Okay, let's look at this collection of matric past paper questions on chemical equilibrium. They past paper questions from 2014 to 2020, all of the supplementary to June exams to the November-December exams. So the first one, a hypothetical reaction reaches equilibrium at 10 degrees in a closed container according to the following balanced equation. A gas plus B gas goes reversibly to AB gas. Delta H is less than 0. So if delta H is less than 0, this reaction is exothermic. Okay. And now it says to you, the temperature is now increased to 25 degrees. Which one of the following is correct as the reaction approaches a new equilibrium? So it's got reaction rate and yield. So the moment we increase the temperature, we always increase the rate of reaction because of reaction rate theory. So we can immediately get rid of D because increasing temperature always increases reaction rate. Now we have to decide according to Chatelier, that dude, according to him, what will happen if we increase the temperature? The reaction that decreases the temperature will be favored. So the forward reaction is exothermic, so we are going to favor the reverse reaction. So we need to decrease the amount of product, so the answer is B. The following reaction reaches equilibrium in a closed container at a certain temperature. 2 ozone go to 3 oxygen reversibly. The pressure is now decreased by increasing the volume of the container at a constant temperature. Which one of the following is correct as the reaction approaches a new equilibrium? So we've got 2 moles of reactants and we've got 3 moles of products. So the reaction, if we decrease the pressure, the reverse reaction is favored. What am I saying? If we decrease the pressure, the forward reaction is favored because the forward reaction creates more moles of gas. So the forward reaction is favored by a decrease in pressure. So what will happen to the number of moles of O3? It's going to be one of these two, C or D, because the O3 is going to decrease. The O2 is going to increase. So we're still left with B and C. What will, however, happen to the concentration of the oxygen? Now, the number of moles of oxygen will increase, but the concentration is going to decrease because the container is larger. So even though there are more moles, the moles per unit volume, which is the concentration, will be less, so it will decrease. So it says the energy changes represented by P, Q, and R on the potential energy graph take place during a reversible chemical reaction. Which one of the following changes will decrease both P, which is the activation energy for the forward reaction, and R, which is the activation energy for the reverse reaction? So what decreases activation energy? The addition of a catalyst. And Q will remain unchanged because Q is the enthalpy, and the enthalpy depends only on the nature of the reactants or the product, so the answer is B. The reaction represented by the balanced equation below reaches equilibrium in a closed container. Chlorine gas plus water liquid goes to the chloride ion aqueous plus, I think that's the chlorate ion, or it's the hypochlorate ion, plus 2 protons in aqueous solution. Which one of the following reagents will favor the forward reaction when added? Now it says here hydrogen. There's no hydrogen in this equation. There's a proton, but there's no hydrogen, so that's not going to do anything unless you count it as adding a gas. Sodium chloride will add chloride ions, but chloride ions are a product, so they will favor the reverse reaction. If you add them, the equilibrium will try to favor the reaction that removes the chloride ions, so it won't be that. If we add hydrogen chloride, That's a double whammy in the water. It's going to add both protons and chloride ions, as it's a strong acid that dissociates strongly. That will favor the reverse reaction. But if we add sodium hydroxide D, the OH minus from the sodium hydroxide will remove these protons here in the form of water, and that will favor the forward reaction. The removal of products will always favor the forward reaction. So here, number 4, the answer is D. It says a catalyst is added to a reaction mixture at equilibrium. Now, what is the role of a catalyst? A catalyst speeds up both the forward and the reverse reactions, but it does absolutely nothing to the yield. So which one of the following statements is false? The rate of the forward reaction increases. That's true. The rate of the reverse reaction increases. The equilibrium position shifts to the right. No, the only way we can shift the equilibrium position is if one reaction is favored over the other, and the catalyst does not do that. So the equilibrium position remains unchanged. So the one that is false is C. Now, question 6, the reaction between hydrogen gas and iodine gas reaches equilibrium in a closed container according to the following balanced equation. Which one of the graphs below shows the relationship between the amount of hydrogen iodide gas at equilibrium and the pressure in the container at constant temperature? Well, if we are at equilibrium, then none of the concentrations of the gases are changing, and there are 2 moles left of gas, 2 moles right of gas in the balanced equation, 2 moles here, 2 moles here. There's absolutely nothing that can happen if you don't change the temperature. So it stays in this lovely steady state of A. Equilibrium means the concentration of the reactions and products remains constant. It says a certain chemical reaction reaches equilibrium at 25 degrees. The equilibrium constant Kc for the reaction at this temperature is 1 times 10 to the negative 4. Well, 1 times 10 to the negative 4 is this number, which is less than 1, which means that there are fewer products than reactants, because remember, Kc is the concentration of the products over the concentration of the reactants. So if Kc is less than 1, there's got to be less concentration of products than reactants. So which one of the following statements regarding this reaction at equilibrium is correct? The concentration of products is equal to that of reactants. No, then Kc would be 1. The concentration of products is higher. No, then Kc would be bigger than 1. The concentration of products is lower than that of reactants. That looks correct. The rate of forward reaction is lower than the rate of the reverse reaction. No, that's rubbish, because the equilibrium definition states that at equilibrium the rate of the forward reaction is equal to the rate of the reverse reaction. So the answer has to be C. Number 8, consider the following chemical reaction at equilibrium in a closed container. 2 mercury oxide solid goes to 2 mercury liquid plus oxygen gas. Now this is interesting in terms of Kc, because solids are 1 in the equation, liquids are 1 in the equation, so the only thing that can make Kc here, if we do Kc as products over reactants, is the concentration of the oxygen gas. That is literally the only thing that makes up Kc here. So it says to you now, more mercury oxide solid is now added to the container at a constant temperature. Now the only thing that can change Kc in any case is changing the temperature. So how will the number in moles of oxygen gas and the value of Kc be affected at equilibrium? Kc is only affected by changing the temperature. So A and D are immediately gone because they say something happens to Kc. We can only look at the answers where Kc remains the same. Now we are adding a solid to something. A solid is not going to do anything to the equilibrium. So the answer is C. We are going to have the same value of Kc because we didn't change the temperature. And because we added a solid, then it does not affect the number of moles of oxygen produced because we haven't changed the pressure or anything like that. Number 9. Which statement is correct for a system in dynamic equilibrium? All reactants are used up. No, that is for a non-reversible reaction, not an equilibrium reaction. The forward reaction is equal to the reverse reaction. This sounds sort of okay, but this is also not in fact okay because it is the rate. The rate of the forward reaction is equal to the rate of the reverse reaction in dynamic equilibrium. It means the change in concentration of products and the change in concentration of reactants per unit time is the same, so B is also wrong. All substances in the reaction are of equal concentration. No, that's rubbish. You can change all of the concentrations of things in the reaction in all different weird ways in an equilibrium reaction. And D is correct. The concentration of reactants and products remains constant because the forward reaction that uses up the reactants is proceeding at the same rate as the backward reaction, which uses up the products. So now we come to one of these lovely graphs. Initially, a certain amount of P gas was placed in an empty container. The hypothetical equation reaches equilibrium in a closed container according to the following balanced equation. P goes to 2Q, and they're both gases. Delta H is less than 0. So this one is exothermic. Okay, this is exothermic. So at time T, the temperature is increased. So an increasing temperature will always increase the reaction rate. So we want to look for a graph where the reaction rate goes up. Okay, but then the thing is we have to decide, will the rate of the forward and the reverse reaction speed up exactly the same amount? If this reaction is exothermic and we increase the temperature, then according to Le Chatelier's principle, the reverse reaction will be favored. Okay, so the reverse reaction will be favored. So the reverse reaction is going to speed up more than the forward reaction. So here it's not actually stated which is the forward and the reverse reaction, but obviously the one that starts at the high rate has to be the forward reaction because P was placed by itself in the container. So the dotted line here is the forward reaction, and this is the backward reaction, the solid line, because obviously the rate of the forward reaction, if there was only P to Q is the only reaction that can happen. So all of these graphs show, okay, this one's not okay, this first one's not okay because at time T, one of the reactions slowed down. We need both reactions to speed up. They can't speed up the same because of Le Chatelier, so D is also out because that would be like what happened if you added a catalyst. D is like what happens when you added a catalyst. So if we increase the temperature, the reverse reaction is favored. So we want number B, this one over here, because can you see both reactions went up, but the solid line went up more than the dotted line. That shows you that the backward reaction has been favored. Okay, number 11, consider the following balanced equation for a system at equilibrium. 2 sulfur dioxide plus oxygen goes to 2 sulfur trioxide. How will the addition of a catalyst, remember a catalyst only speeds up the reaction rate of both the forward and the reverse reaction. So we're going to get rid of this one because the catalyst always speeds up the rate of reaction. And what will happen to the yield? It does absolutely nothing to the yield. The answer is C. The yield remains the same, although the reaction rate increases. You are not going to produce any more sulfur dioxide or sulfur trioxide in comparison. You will just produce the same amount a little bit faster. Here we get to number 12. A hypothetical reaction reaches equilibrium at a certain temperature in a closed container according to the following balanced equation. A gas plus 2B gas goes to 3C solid with a delta H that is less than 0. So this one is also exothermic. Which one of the following changes to the equilibrium concentrations will result in an increase in Kc? Now the only thing that changes Kc is temperature. So we are going to immediately get rid of C and D because the only thing that changes Kc is temperature. So if we want to increase Kc, Kc is the concentration of the products over the concentration of the reactants. So how would we increase the products? We have to favor the forward reaction. So we have to decrease the temperature because only a decrease in temperature will favor the forward reaction. Chromate ions, which are yellow, and dichromate ions, which are orange, are in equilibrium with each other in an aqueous solution according to the following balanced equation. Can you see here? 2 chromate ions plus 2 protons goes to the dichromate ion plus water, which is liquid. Which one of the following reagents should be added to change the color of the solution to yellow? So to make it yellow, we want to favor the reverse reaction. Now just have a look here at A, B, C, and D. This is an acid, this is an acid, this is a base, and this is an acid. So who is the odd man out here? It is C, the base. So my brain is telling me that I think that the answer should be C, the sodium hydroxide. But let's see if we can find a logical reason for this. And the logical reason is if we want to favor the reverse reaction, we can do that by either adding more products or removing some of the reactants. So H plus the OH minus from the sodium hydroxide is going to give me water. It's going to remove a reactant. So the equilibrium will shift to try and replace the reactant. So the answer is definitely C, adding sodium hydroxide. Number 14. Which one of the descriptions below is true for a chemical reaction in equilibrium? So we want anything that says the rate of forward reaction and reverse reaction is equal, because that is what your definition tells you. At equilibrium, the rate of the forward and the reverse reaction are equal. So we've handily got rid of the two answers. What happens to the concentration of reactants and products? They remain the same. They are not equal. You can put any different values of reactants and products in a container for a chemical reaction. So you can end up with any kind of final concentration of reactants and products. But when we are in equilibrium, the concentration of those will remain the same unless something acts on the equilibrium. Here we have another reaction reaching equilibrium in a closed container. Nitrogen gas plus 3 hydrogen gas gives me 2 ammonia gas plus energy. This is the other way of stating this reaction is exothermic if we have energy as a product. Consider the following statements regarding the equilibrium. Which ones are correct? So let's look for correct statements. Okay, so at equilibrium, the rate of the forward reaction equals the rate of the backward reaction. So when one nitrogen molecule combines with 3 hydrogen molecules, 2 ammonia molecules decompose at the same time. This is true because that means the rate of the forward reaction is proceeding at the rate of the backward reaction because these are in their stoichiometric concentrations as per the balanced equation. An iron oxide catalyst increases the amount of ammonia produced. No, catalyst does nothing to the yield. It just makes you reach equilibrium faster, so that is wrong. When the temperature increases, the equilibrium constant will increase. Now the forward reaction is exothermic, so if we increase the temperature, we actually favor the backward reaction. So this is not going to help because for Kc to increase, we need to make more products. So this one is also wrong because increase in temperature favors the backward reaction. So I get A, 1 only. Now number 16, study the following reaction at equilibrium at a certain temperature. 2 sulfur trioxide goes reversibly to oxygen plus 2 sulfur dioxide. Delta H is greater than 0, so this is an endothermic reaction. Which one of the following factors will change the Kc? The only thing that changes Kc is the temperature. So adding more reactant will not help. Adding a catalyst will just speed up the rate of reaction. Increasing the pressure is going to do nothing. The only thing that changes Kc is changing the temperature. So the answer is C. Number 17, the reaction given below reaches equilibrium in a closed container. The Kc value is 0,04. This is a fraction, which means that we have less products. Remember, 0,04 is the equivalent of 4 over 100. So this means that we don't actually have that many products. If delta H is less than 0, this is exothermic, the forward reaction. Which one of the following factors will change the Kc value? We want to increase the Kc value because this is 4 over 10, which is bigger than 4 over 100. So we need to do something to change Kc. The only thing that changes Kc is temperature, so ignore those other two answers because it's got nothing to do with Kc. And then we have to decide this reaction is exothermic, but we want to favor the forward reaction, so we need to decrease the temperature because that is all that will favor the forward reaction so that we can have more products. Number 18, which one of the following statements best describes a state of dynamic equilibrium? The limiting reagent has been used up. No, limiting reagent is a concept that belongs with non-reversible reactions. The forward and reverse reactions have stopped. No, remember it is a dynamic equilibrium. The reactions are proceeding but at the same rate. This looks correct. C. The concentration of products equals the concentration of reactants. No, you can put anything in your container at any original values and they will just keep changing until equilibrium, and then they can be at any random value depending on what random thing you put in the container to begin with. So the only one that is correct is at dynamic equilibrium, the rate of the forward and reverse reaction are equal. Number 19, the graph below shows a change made to a chemical equilibrium in a closed container at a time T1. The equation for the reaction is, okay, this is the Haber process. Nitrogen plus hydrogen gives me 2 ammonia, and it's an exothermic reaction. Delta H is less than 0. So now this is not the world's best graph, but if you have a look here at time T1, can you see that there is a gradual change here, a gradual change here, and a large change here? Okay, so we can see that the amount of ammonia produced increased, the amount of hydrogen decreased, but the amount of nitrogen sharply increased. So if we added a catalyst, the hydrogen and the nitrogen, everything would have changed, but the hydrogen and the nitrogen would both be dropping and the ammonia would be going, no, it wouldn't. If we added a catalyst, the rate of the forward and the reverse reactions would speed up, but nothing would happen to the concentrations. If we increased the temperature, all of the reaction rates should have increased, except some would have increased more than the others because of the delta H. So all of the graphs would have changed fairly dramatically. Not just this one has got to be C. There's an increase in the concentration of ammonia because that's of nitrogen, sorry, because this graph is the only one that went up so sharply, and then everything else reacted because if we added nitrogen, the forward reaction would be favored, and then we see this corresponding uptick in the production of ammonia with the decrease in hydrogen. But we did not increase the pressure. If we increase the pressure, then it's the same as increasing the concentration in terms of reaction rate, and everything would have been shooting up, and then some of them would have shot up more than the others. It's only really the nitrogen that shot up, so it has to be C. Now consider the equilibrium constants for the same reaction at two different temperatures. So this temperature here is a low temperature. This is a high temperature because it's 298 Kelvin versus 318 Kelvin. And if we have a look here, this Kc is got a bigger Kc. There is a bigger Kc because 0.03 is bigger than 0.05. So there is a bigger Kc at a lower temperature. So which one of the following is correct? The yield of products as the temperature increases. Now remember, Kc is equal to the concentration of the products over the concentration of the reactants. So this one at the high temperature has a much lower products. So we're looking at the answer, one of these two, because both of them have decreased, okay? Shows a decrease in the amount of products at a higher temperature. What is delta H? If a higher temperature is favoring the reverse reaction, that means the reverse reaction must be endothermic, which means the forward reaction must be exothermic, which is a delta H less than 0, which means that this is B, because increasing the temperature favored the reverse reaction, which made reactants, which made the Kc drop. 21. The balanced equations for three reactions at equilibrium in a closed container are given below. In which reaction will the equilibrium position shift when the volume of the reaction vessel is decreased at constant temperature? So now this one, when we are decreasing the volume of the reaction vessel, it's the effect of increasing concentration. And when we look at the change in size of the reaction vessel, we have to look at the moles of gas on the left and the moles of gas on the right. Okay, so in this first reaction, I've got 1 mole plus 1 mole, 2 moles of gas on the left goes to 1 mole of gas on the right. In this one, I've got a solid. Changing the thing is going to do nothing to that. Changing the volume, there's another solid, and then I've got 4 on the left and 4 on the right. And in the last equation, I've got 1 and 1, 2 moles on the left, and 1 and 1, 2 moles on the right. So only in reaction 1 will changing the pressure change the equilibrium position, because according to Chatelier, the system wants to do something to counteract the change that you made, and it's going to do nothing in 2 and 3 because there's no benefit to either the forward or the backward reaction, because the moles of gas on the left-hand side and the moles of gas on the right-hand side are the same. So the answer to 21 is A, 1 only, because there's 2 moles of gas on the left to 1 mole of gas on the right. And that brings us to the last of these equilibrium questions. Initially, 2 moles of carbon monoxide and 2 moles of hydrogen are sealed in a container. The reaction reaches equilibrium according to the following balanced equation. 1 mole of carbon monoxide plus 2 moles of hydrogen give me 1 mole of methanol gas. At equilibrium, the amount of methanol in the mixture will be. Okay, so now if this were a non-reversible reaction, if you have a look here, I've got 1 mole of carbon monoxide to 2 moles of hydrogen. So according to this, the hydrogen, if it were an ordinary reaction, the hydrogen would be the limiting reagent, okay? So with 2 moles of hydrogen, the molar ratio gives you 1 mole of the, what do you call this, methanol, okay? But the problem is this is an equilibrium reaction. So while 2 moles of hydrogen will produce 1 mole of methanol, the equilibrium is not going to lie completely to the right. This is not a reaction which only has the forward reaction. It is a reaction that has a forward and a reverse reaction. So 2 moles is way out of order, and so is greater than 1 mole, because basically the hydrogen is kind of a limiting reagent here, okay? But we are going to have C less than 1 mole because we know this is a reversible reaction. So some of the products that we make will immediately go back to reactants. So although the things combine in the stoichiometric ratio, you will find that at equilibrium you will have less than 100% yield of the forward reaction. Number 23, which one of the following will not affect the equilibrium position of a reversible chemical reaction? Well, here, whenever you see something that we're adding to an equilibrium thing and it's not affecting the position, my answer is going to be a catalyst, okay? Why is temperature wrong? Temperature will favor the endothermic reaction in a reversible reaction. So if you favor one reaction over the other, you affect the equilibrium position. With pressure, it depends on how many moles of gas are less on the left or the right. And with concentration, the same thing. These two have the same effect, and we don't know enough about it. These can affect a reaction. They may not affect the equilibrium position, but the only thing that will never ever affect the equilibrium position is the presence of a catalyst. Now we have here, consider the equilibrium represented by the balanced equation below. 2 chromate ions plus 2 protons go reversibly to the dichromate ion plus water. Delta H is less than 0, so this forward reaction is exothermic. And so if it's exothermic, let's have a look here. Which one of the following changes to the equilibrium will favor the forward reaction? So to favor the forward reaction in terms of temperature, if the forward reaction is exothermic, a decrease in temperature is going to favor the forward reaction. So we can get rid of these two because a decrease in temperature will favor the forward reaction. And now it says increasing the pH or decreasing the pH. So now remember, pH depends on the concentration of your hydronium ions, okay? So if we increase the pH, it means a decrease in protons, whereas a decrease in pH means an increase in protons. And the protons are here on the left-hand side. So if we add more protons, we will favor the forward reaction. So which one causes an addition of protons? A decrease in pH increases the number of protons, which will favor the forward reaction. So the answer is B. You add hydronium ions and you decrease the temperature, and the forward reaction will be favored. And that is the last question here.